Hello, everyone. In this lesson, we will learn about the main circuit. First, let's take a look at the main power circuit. The equipment uses a 380 volts, 3-phase 4-wire power supply with a 4-pole connector. After connection to the power source, let's look at the main power switch, which is a 3-phase 4-wire circuit breaker. The power flows through several parallel connected indicator lamps, and then to the emergency stop switch, and finally to L1, L2, L3, and the ground N. According to the circuit diagram I shared with you, once the current flows down, it reaches the fuse and then flows to L21, L22, and L23. First of all, we must ensure that the fuse is in normal and good condition. We can inspect it as follows. Push the switch downward and take out the fuse for inspection. To inspect the fuse, use a multimeter. Turn the multimeter selector knob to the continuity mode, buzzer mode, and test for continuity across the fuse terminals. If the fuse is intact, the multimeter will emit a beeping sound. If there is no beep, it indicates that the fuse is damaged. This is a simple method for fuse inspection. We must ensure that the fuse is in good condition. After inspection, reinstall the fuse and push the switch upward to restore the normal current circuit. After the current flows out, it passes through L21 and L23. Referring to the circuit diagram, the current first flows through positions 1, 2, 3, and 4 of the terminal block, which correspond to L21, L22, L23, and ground N. After the current flows through L22 of the terminal block, it goes to the main AC contactor K, supplying power to the main contacts L21, L22, and L23 of the AC contactor. The current then flows out to L31, L32, and L33, forming a continuous circuit path. After leaving L31 and L32, the current bridges through the terminal block and reaches L13, L14, and L15. Where does the current go next? It flows to the intermediate relay KA1, energizing its L1, L2, and L3. When the relay coil is energized, the current flows out from this point and becomes L41, L42, and L43. Next, we will use a multimeter to inspect whether the wiring follows the expected path. Insert the black probe into L1 and the red probe into the relay terminal. If the multimeter's buzzer sounds, it indicates that the circuit is normal. This method can also be used for multi-wire testing, for example, from L2 to L22 of the terminal block, from L3 to L23 of the terminal block, and from ground N to the grounding position of the terminal block. By following this wiring check procedure and properly using the continuity buzzer mode of the multimeter, we can avoid unnatural damage to the circuit or human errors such as poor wiring connections. Continue the inspection. At L21 of the terminal block, lift the white cover on the top and connect the multimeter between L21 and the main AC contactor K. The buzzer will sound if the connection is correct. If the multimeter is connected to the same wire, it will not beep. It only gives a signal when two different points are connected. Similarly, check the connection from L31 to positions 13, 14, and 15. Lift the white cover on the top of L31. When current flows to the positions, the multimeter should emit a beep. From positions 13 and 14, the current then flows to position 32. Perform the same check on position 33. If the multimeter beeps, the wiring is normal. Next, after the current flows out from L41, L42, and L43, where does it go? It is directed to the variable frequency drive, VFD below, serving as the main power supply for the VFD. The green wires I'm holding are the signal wires of the VFD, while the ones inside are the VFD's main power wires. We can check the internal wires 41, 42, and 43 of the VFD. First, let's check wire 41. It shows continuity. Then check wire 42. Connect the second wire. Finally, we check wire 43. It should also show continuity. This provides the VFD with its main power supply. After passing through the VFD, the current flows out through 3 wires: U1, V1, and W1. So, where are these 3 wires connected? They are connected to the thermal relay. Once connected to the thermal relay, they provide overload protection. When the multimeter probes are placed between U1 and the corresponding terminal, a buzzer sound confirms the overload protection. From there, the output becomes U21, V21, and W21. According to the power supply circuit, these 3 wires continue to terminal block 2 at positions 1, 2, and 3. From positions 1, 2, and 3, the current passes through the main power contact point to supply power to the main motor, forming the main power circuit. In other words, the current flows out from here, then connects to positions 1, 2, and 3 of terminal block 2, and finally connects to the main motor circuit, completing the control circuit for the main circuit. Everyone, please try tracing the wiring based on the circuit diagram and wiring diagram I shared with you. In the future, when you work in a company, you might only be given a circuit diagram and asked to complete the wiring on your own. Sometimes the wires are not connected yet, or in cases of equipment maintenance or faults, the first step is always to read and understand the circuit diagram and figure out how the circuit is wired. This is the main power circuit. Alright, now let's move on to the second circuit, the control circuit for the main circuit. So, how is it wired? Let's look at the wiring diagram in your hands. According to the wiring diagram, the general wiring goes like this. First, one phase is taken out from the 3-phase supply at L21 and used as the power supply of the control circuit. It is connected to terminal 8, and the ground wire is also connected to terminal N9, position N0. These two serve as the control circuit wires. Then, the wiring exits from terminal 8, L21, and connects to the input side of the main power switch SK1, which is located at the back of the equipment. The SK1 input is the main power switch. Let's open the cabinet door to see the actual wiring. Here's how it is wired. Wire 8 first enters the point indicated by my finger. After exiting from the input side of SK1, the signal is referred to as the SK1 output. The SK1 output splits into 2 branches. One branch first goes into the emergency stop switch. After leaving the emergency stop switch, it becomes SB1. SB1 is then routed to the normally open switch and connected to the stop button SBS, becoming SBS. SBS is also connected to the start button, and after leaving the start button, it becomes SBT, which then continues outward. The other branch of the SK1 output passes through SBS and then reaches the point indicated by my finger, where 2 indicator lamps are located. These 2 lamps are designated as HL1 and HL2, and the circuit then returns to the control panel on the front side of the equipment. From the start button on the back of the equipment, the wire connects to wire 5, SBT. SBT goes down through the coil to the main contactor terminal I2. From I2, it exits to the main coil terminal I1 and returns to the neutral wire. The other 2 lamp wires are connected to positions 10 and 12. The outputs from positions 10 and 12 connect to 2 contacts, one normally open and one normally closed, and then return as N1 and N2 to positions 9 and 11, finally returning to position 4 and back to the neutral wire. Now, let's review the complete power supply logic of the control circuit. First, turn on the main power switch to energize the equipment. When pressed, the stop indicator light turns on. Then, release the emergency stop switch. Next, press the start button, and the whole power supply begins to operate. This is the complete power supply logic, the complete control circuit for the main circuit. Now, let's move on to the third circuit, the 24 volts power supply circuit. This equipment operates on 220 volts and 380 volts AC. However, components like the PLC and the touchscreen require a 24 volts DC supply. So how is this voltage conversion achieved? According to the wiring diagram, a wire branches out from L31, goes through terminal 13, and then connects to terminals 16 and 17, with a ground wire also connected. From the junction at L31, the wire connects to the power switch panel below. The function of the power supply switch is to convert 220 volts AC into 24 volts DC. The input of the power switch is L31 and N, and the output becomes 0 volts and 24 volts. Then, the 24 volts wire connects to terminals 27 and 28, supplying power to all components that require a 24 volts power source. Next, let's test using a multimeter to verify that the wiring matches the described circuit. First, test the 2 points on the upper terminal block. Then, test for voltage at L31 and the switch panel. A multimeter beep confirms power is present. Similarly, verify the neutral wire from the upper block back to the panel, confirmed by a beep. Next, check the 24 volts output by probing the 24 volts wire at the switch and terminal 27. A beep indicates continuity. Finally, check the bridge connection at 25 and the 0 volts wire. All produce normal beeps. Note that this 0 volts DC is unrelated to the AC or DC neutral wire mentioned earlier. They are isolated. The multimeter did not beep between them. The 0 volts DC wire is an independent reference point, and continuity will only be detected within the DC circuit. This means the black AC live wire and the neutral wire are separate circuits. The AC neutral wire may still carry current. That's the basic wiring of the 24 volts power supply circuit. Now let's continue with the main circuit, the power supply circuit for the VFD servo motor. First, the servo motor draws power from L32 and L33, passing through terminals 13, 14, and 15, and branching to this point. It then goes through a jumper at 18 and 19, exiting again at L32 and L33. Next, it connects to K, where the 2 wires carry 380 volts AC, which enters the intermediate relay Ki2, and then passes through terminals 32 and 33 to L52 and L53. From L52 and L53, the wire enters a transformer, the black transformer located at the bottom of the equipment. The transformer receives 380 volts AC and outputs 220 volts AC. L and N. These L and N wires are connected to the power inputs of the 2 servo drivers, indicated by my finger. After conversion by the servo driver, 4 wires are output: U, V, W, and a ground wire. The ground wire is connected to the servo motor via a connector, as shown in my hand. Now, let's verify the wiring using a multimeter. Power passes through 32 and 33, branches to 18 and 19, then goes downward, becoming 52, and continues to the transformer. After the transformer, power is converted by the servo driver into a 3-phase output. The main function of this section is to provide the servo driver with an independent, isolated power supply, free from interference from other circuits. Next, let's check the 3-phase wiring, these 4 wires going to the servo motor. The servo motor here is used for the x-axis, and we use a multimeter to test the connections from the x-axis to U, V, and W. The first wire makes the multimeter beep normally. Then, the second and third wires also show normal readings. Finally, the ground wire test is normal as well, which means the power supply test is complete. After that, connect the 2 ends of the servo motor adapter together to provide the servo motor with a stable power supply. This completes the power supply circuit for the servo motor. Alright everyone, let's move on to the next part, the low voltage power supply for the PLC and the touchscreen. Although this looks simple, the actual wiring is quite complex. First, the 24 volts output from the power supply goes through the switch panel and connects to L27 and L28, where L27 equals 24 volts and L28 equals 0 volts. However, you'll notice that the PLC side shows 24 volts V2. And if we try to bridge from 24 volts to 24 volts V2, the circuit will be open, indicating no connection. Connecting the multimeter between 24 volts and 24 volts V2 produces no beep, which indicates that the 2 points are not directly connected. So how does the actual circuit work? The wire from L27 and L28 goes to the main power switches at the back of the equipment. There are 4 switches on the panel: system main power switch, AC motor power switch, stepper motor power switch, and servo motor power switch. With the panel opened, observe the first switch. The 24 volts supply from terminals L27 and L28 on the front panel enters at this point. After passing through the switch, it emerges as 24 volts V1. V1 is divided into 2 branches. One branch goes back to SI3 of the PLC and splits into 3 wires, which come out from the second, third, and fourth switches, namely SI2, SI3, and SI4. The other branch is connected in parallel with an S24 volts V1, which then goes to L29 and L30 of terminal block 1. From L29, the 24 volts V1 goes to KA3. KA3 first passes through to this position, powering the KA3 coil. At the same time, another branch directly connects to the 24 volts V1 of KA3. Once the coil is energized, the output becomes 24 volts V2, which is the actual supply line for the PLC. Testing with a multimeter confirms that the 24 volts coming from the backside is not conducting. However, 24 volts V1 is connected in parallel to this point, and the multimeter shows a normal reading. There are 2 wires, the other one goes to 24 volts V2, where the multimeter shows no continuity. But at KI3 it does show continuity. When the current from the output position is connected to KI3, the multimeter reading is also normal. In the actual circuit, the current also passes through KI2. If the KI3 coil is activated, it provides 24 volts V2 to the PLC. So the PLC is actually powered by 24 volts V2. Meanwhile, the touchscreen uses 24 volts V1. 24 volts V1 also branches to terminals 37 and 39, and the 0 volts wire connects to 38 and 39. All continuity tests are normal. This is the PLC power supply circuit. When the system is powered on, we go to the backside and turn on the main switch, then switch on the power supply system, and finally turn on the AC motor. As for the other AC motor and the stepper motor, since the 24 volts V1 supply here is divided into switch 2, switch 3, and switch 4, once all 3 switches are closed, SI1, SI2, and SI3 are all activated. SI1 is located here. SI2 continues on to this point, where it is referred to as 31. From 31 it becomes KI1, which powers coil 1. Once coil 1 is energized, it pulls in and allows this contactor to conduct. For KI2, the output from KT2 goes through SI2 and SI1, then SI4. SI4 connects here, and it supplies power to KI2, which energizes the servo motor coil. Then there's SI3. After SI3 is activated, it is referred to as V positive, and V positive is directly connected here at the bottom to power the stepper motor. When the voltage reaches the stepper motor, a coil inside is energized, and similarly, the stepper motor is supplied with power.